Hi everyone. In this session, I talk about my tool, FN-Fuzzy. That is first multiple binary diffing triage tool for IDA Pro. I'm Takahiro Haruyama. I'm a senior threat researcher with Carbon Black's Threat Analysis Unit, TAU. My mission is reverse engineering cyber espionage malware linked to mainly China, Russia, and North Korea. Formerly, I presented some researches at security conferences such as VNTI, PlugX Research, anti-forensic analysis methods, memory forensic tool, and so on. This is today's overview. First, I explain the background and motivation of my tool. Next, I show how to implement my tool and demonstrate it. After that, I evaluate the tool's performance and accuracy. Finally, I wrap up my presentation. First, I explain the background. I think IDA Pro is the de facto disassembler for malware reverse engineers. We can save our findings into the database file called IDB, then import the findings when analyzing new malware variants. But if there are a lot of IDBs, the importing task is not easy. For example, in my case, I don't remember the code that I analyzed a few years ago. In that case, I need to identify the most similar and analyzed IDB to be imported from large sets of IDB. In order to do that, there are some binary diffing tool. InFuzzy-based binary diffing tool, function-level binary diffing tools for IDA Pro. In function-level binary diffing tools, they are separated into two categories: one-on-one comparison tools and one-to-many comparison tools. From this slide, I explain the existing tools. InFuzzy for Neo4j is published by JPSAT. InFuzzy is the SSD value of API function names in Windows PE formatted executables. Neo4j is a graph tool. It visualizes malware clustering based on InFuzzy values like this. Each distance stands for the imported function name similarity. So if the distance is very close, we can say they are almost the same samples. InFuzzy for Neo4j is handy to detect binary similarities very quickly, but it's not available for Mac and Linux malware, and it's not effective for malware resolving API function addresses dynamically. Additionally, we are not sure which sample is most analyzed in IDA Pro, because InFuzzy for Neo4j does not contain IDB information. As function-level binary diffing tools for IDA, there are several IDA Pro plugin or IDA Python scripts. BinDiff is a widely used IDA Pro plugin. The Horror is an IDA Python script supporting the compiled code diffing, and the development is very active. BinGrep, the unique point is providing multiple candidates for each function. All tools compare binaries one-on-one, so we need to write wrapper scripts for multiple binary diffing. So I wrote a wrapper script for BinDiff 4.2 before. The behavior is very simple. BinDiff calls two scripts. One generates bin export file from IDB. The other saves function names. And the BinDiff executable accepts bin export file and creates .bindiff result file. And the BinDiff receives .bindiff file and function names and output the result. The wrapper script output is like this. It displays similar binaries. Other than that, similar functions. About performance, 100 samples comparison took 300 to 800 seconds on my analysis VM. So I don't think the wrapper is scalable for hundreds or thousands samples. Besides, BinDiff is closed source software, so we can't fix the bugs for ourselves. Actually, in version 4.3, when importing multiple function information, I got an error like this, so I could not do that. And other bug is when saving BinDiff file, then open it, the confidence and similarity values are swapped. The bugs have been resolved in version 5.0, but 5.0 has another bug, and it's critical for multiple binary diffing. So I searched for other tools for my purpose. I'm not sure how to read it. KAM1 and 0. In this presentation, I read it Camino. Camino is one-to-many sample comparison tool with Python plugin. The latest analysis engine has high accuracy for all options applied in obfuscator LLVM, according to the web page. Obfuscator LLVM is a kind of obfuscating compiler. So I tested the APT10 malware obfuscated by an unknown obfuscating compiler. For example, function is obfuscated with the unknown compiler like this. The obfuscation techniques, opaque predicates, and control for flattening are used by the sample. As a result, Camino could detect original functions of the obfuscated function. In this screen, Camino reports the obfuscated function has about 70% similarity with the original not obfuscated functions. But instead of the high accuracy, 20 samples comparison takes over 1 hour. So I guess Camino requires high-spec machines. My motivation is I'd like to use function level binary diffing tool to identify the most similar and analyze the IDV from large sets of IDV, then import the findings quickly. I hope to do that less than 1 minute. And it does not require high-spec machines. So that's why I created a new tool. FN fuzzy calculates 2 kinds of fuzzy hashes for each function. One is SSDIP hash value for extracted code bytes. The other is, I'm not sure how to read it again, but I read it, Machok. Machok hash value for call flow graph. All hashes are saved into one SQL database file, then used for comparison. We can import function names and prototypes from multiple IDVs at one time. And structure type information defined in function prototype can be imported as well. I guess most people know what SSDIP is, so I just explain why I use SSDIP for FN fuzzy. First, SSDIP is the de facto standard fuzzy hashing algorithm. It's originally from spam email detection, but not limited to text data. Second, SSDIP is fast. It's twice as fast as TLSH. Third, SSDIP does not require minimum size for input data. On the other hand, for example, SD hash requires 512 bytes for input. SSDIP does not define the minimum size, though it outputs the warning. For SSDIP hash calculation of extracted code bytes, I reuse the modified version of Yara FNPy. Yara FNPy is an Python script to define a Yara rule based on code bytes of a function. The modified version calculates fix-up code size correctly, and it excludes not only fix-up bytes, but also other operand data, like direct memory reference, immediate value, register displacement, near and far calls. So the extracted code bytes can be more generic. For example, in this function, there are several code bytes to be excluded. For example, this is immediate value, fixed up code bytes, direct memory reference, register displacement, near call. So the related code bytes will be excluded, and the remaining code bytes will be concatenated into one byte sequence and calculated for SSDIP hash. By the way, the SSDIP score for small data sometimes drops sharply. For instance, they are almost the same function, except a few code bytes difference. But the SSDIP score is 33. It's much far from the complete match 100. In order to correct abnormal SSDIP score, FN fuzzy calculates matrix hash values of call flow graphs. What's matrix hash? Matrix hash is a simple fuzzy hash mechanism based on the call flow graph of a function. Let's see this call flow graph. The call flow graph will be translated into these strings. Each line means basic block 1 has destination basic block 2 and 3. Basic block 2 has no destination. Basic 3 has destination 4 and 10. Basic block 6 has destination 7, and it contains call instruction. So character C is inserted. Finally, they will be concatenated into one string, then hashed to produce a 32-bit output. FN Fuzzy uses MAMA hash 3 to produce the 32-bit hash value. I implemented FN Fuzzy with IDPython and the wrapper script. FN Fuzzy is an IDPython script to export or compare hashes of one binary on either GUI. CLI export py is a wrapper script to export hashes of multiple binaries. FN Fuzzy requires two Python packages, MAMA hash 3 and Python IDB. Please note, FN Fuzzy only supports IDBs generated by version 6.9 or later due to SHA-256 API usage. We can check the IDE version by running this Python command. From this slide, I demonstrate my tool while explaining execution options. Just a moment. Much bigger than I expected. The execution options are separated into 4 categories: general options, command options, export command specific options, compare command specific options. In general options, DB file path is a SQLite database file path to read-write hash values. Minimum function code size is a threshold to limit hash calculation. If function code size is less than the threshold, by default, the value is 16 bytes. The function will be excluded for hash calculation. And FN Fuzzy also provides an exclusion option for library and thunk functions by using either flat signatures. And this is the debug message option. And in this demonstration, I'd like to compare hash values. So in command options, I select compare. Export and compare options are mainly related to performance and similarity threshold. I'd like to explain performance options first. Needless to say, if there are a lot of functions, the hash comparison computation will cost a lot. We compare Y hashes against the database containing X hashes. The computation will be OXY. So in order to reduce the computation cost, FN Fuzzy provides 3 performance options. First, compare with only analyze the functions. Usually, after analyzing a function, I rename the function with prefix string fn another like this. So if the specified prefix string or suffix string is included in the function name when exporting hash values, and check this option, fn fuzzy saves flag information as an analyzed function, and it will be used in compare command. If you check this option, compare with only analyzed functions. By default, the option is enabled because basically I'm not interested in functions that I didn't analyze before. The second performance option is straightforward. Just specify the folder path, then fn fuzzy compares with only IDBs in the specified folder. The third option is related to code size. Each hash comparison only targets hashes with similar size. By default, the value is 40. That means fn fuzzy compares a function with its 60% to 140% size hashes. So now run the compare command. Probably it will take 20 to 30 seconds. Just a moment. So if the compare command is finished, fn fuzzy displays the summary tab, including the detected similar IDBs. Each line means the binary share 256 hash value and total similar functions number and analyze the similar functions number. In this demonstration, I checked the option compare with only analyzed functions. So the number is matched with total one. And the IDB path, by the way, fn fuzzy counts multiple similar functions per each function comparison. For example, sub1 is compared and 3 similar functions are detected. Sub2, sub3, fn2 sum. So it contains prefix string, so it's analyzed. In this case, number 3 will be added to total similar functions number, and number 1 will be added to analyze the similar functions number. So please note the total similar functions number may be more than the actual function number. And when we would like to check the detected similar functions in specific IDB, when double-click one of the lines, and the details tab will be displayed. Just a moment. Like this. The details tab contains detected similar functions information. Each line means SS deep score, matrix hash, matched or not, primary function name. Primary function name means function name currently opened in the IDB, and the primary function code byte size. Secondary analyze the function name. That means analyze the function name with the highest SSD score for primary function, and secondary function prototype. We can select the lines. Just a moment. Then right-click, import function name and prototype. Then the information will be imported. And if structure type in function prototype is not defined in the currently opened IDB, FN Fuzzy can import type information after warning message. Yeah. Like this. And structure information is imported like this. Demo is done. And last but not least, I'd like to explain the similarity threshold options. FN Fuzzy detects similar functions matching with one of the following three conditions. First, if SSD score is more than the threshold, by default, the value is 50. The functions will be detected. Other than that, if SSD score is more than the threshold, by default it's 10, and matrix hash is matched, they will be also detected. The third condition sounds a little bit strange, but even if SSD deep score is 0, if match hash is matched and function code byte size is more than the threshold, by default, it's 100 hexadecimal bytes, the function will be detected. The third condition is provided for detecting polymorphic function. For example, fancyware X-agent variant has a polymorphic deobfuscation function like this. And the arithmetic logics and the immediate values are changed per sample. So that's why the SSD deep score will be 0, but the code flow graph is exactly the same. So the third condition can detect the similarity. The condition may also detect similarities between different architecture samples, but I'm not sure. I evaluated the tool's performance and accuracy. I used over 700 IDVs to create the database. In export command, it took about 2 hours. But we need to do that just once, so it's no problem. And in compare command, I compared one C++ sample, including 900 functions with the created database. It took 20 to 30 seconds for analyze functions only, or it took 3 minutes for all functions. So it's much faster than the existing binary diffing tools. About accuracy, I tested 3 cases. One is update variant. I used fancyware X-agent samples. Sample A is old, sample B is new. And compare sample B with sample A. Sample A, IDB contains about 70 analyzed functions. I manually checked the results generated by BinDiff and FNFuzzy. In BinDiff, I checked all functions whose similarity is more than 0.7. In FNFuzzy, I checked the functions detected with default similarity threshold options. Overall, BinDiff is better than FNFuzzy. Total detected similar functions, BinDiff is 42, FNFuzzy is 35. False positives, BinDiff is 1, FNFuzzy is 2. And false negatives, BinDiff is 7. And all 7 functions could be detected by FNFuzzy, and vice versa. FNFuzzy false negatives is 15. So I analyzed the causes about false negatives. Mostly, BinDiff does not accept duplicate matching for secondary functions. If one match is incorrect, the other will be incorrect too, like domino effect. The remaining 3 functions were just missed, I guess. In FNFuzzy, 3 functions were excluded due to small code byte size. 2 functions were missed because they were obfuscated. And 1 function was excluded because it was detected as a library function because the float signature is not correct. The remaining 6 functions were just missed. In the second case, I used the APT10 NL samples. Sample A is not obfuscated, and sample B is obfuscated with compiler level obfuscations, as I mentioned earlier. BinDiff detected 3 similar functions. On the other hand, FNFuzzy could not find at all. 1 function found by changing one of the execution options, but it's a trade-off between accuracy and performance. And some functions are not obfuscated, actually, but call flow graphs changed due to more call instructions. Machoke hash calculation splits basic block by call instructions. That's why they were missed by FNFuzzy. In the third case, I used shadow hammer backdoor sample. The sample contains a unique decoding function. The algorithm was seen in Travex type 1 sample or WinNTI sample. So I checked whether all the 2 functions could be detected or not. Unfortunately, all tools, FNFuzzy, BinDiff, Diaphora, and Camino, could not detect the similarities. I guess Travex type 1 function has different code bytes and call flow graph. That's why it was missed. And about the similar WinNTI code, it was just a small part of the big function. So that's why it was also missed. I think new algorithm may be required to detect that kind of similarity. I wrap up my presentation. FNFuzzy is a fast and lightweight binary diffing triage for large sets of IDV. BinDiff is still better in accuracy because FNFuzzy just depends on 2 kinds of fuzzy hashes. But FNFuzzy provides a high-speed comparison. So I recommend to use FNFuzzy as a triage tool to narrow down the most similar and analyzed IDV to be imported before one-on-one binary diffing like BinDiff or Diaphora. The code is already published on GitHub, so please check it. I have 2 future works. One is extracting more generic code bytes. For example, Hexways provides function prologue epilogue detection API. So by using the API, fuzzy can exclude the function prologue, epilogue code bytes. And another feature work is microcode-based fuzzy hashing. Microcode is an intermediate language for IDA Pro. By using microcode, fuzzy may be able to detect compiler level obfuscated functions like Camino. And there are the references. That's it.